So let me know if the screen is visible.
Yes, sir.
Okay, great. Thank you. So we defined yesterday a random variable, which is nothing but a function which maps us from sample space onto a real number space. We discussed that random variable can be discrete or continuous. Depending on that, if a random variable is discrete, then we talk of the probability mass function, which is nothing but the set of probabilities values at those discrete points of the random variable. We also discussed about the cumulative distribution function and how it is right continuous and other properties of it in one of the examples. We will have to remember that PMF, the probability mass function, itself is probability. That Pxk gives us the probability. It is probability itself. Yeah. Now, when we go to continuous random variable, that means that the random variable can take real values. In that case, we define something what we call as the probability density function PDF. PDF gives probability in the sense that the probability in a small interval dx is equal to px times dx. So px itself is not probability, it provides us or it gives us probability. And then we have the continuous case for the cumulative distribution function. The normalization, of course, for the discrete one is the summation over all discrete values, whereas that for the continuous one is the integration over all x values. And of course, I mean, in the end, we also did that the cumulative distribution function accordingly for the continuous case is given as an integral going from minus infinity to x px dx. So this is what we were doing. Uh, One thing in the continuous interval, which I would like to ask, can we get CDF or PDF from CDF? Can we get probability density function from the CDF? So what would be the formula for getting PDF from CDF? So given a CDF, let's say you are given,
Sir, it is differentiate. To differentiate the CDF, then we'll get PDF.
right? So if you do d of fx over dx, then this provides this probability density function. So at times you will find out that if the CDF or the cumulative distribution function is given, then you may be asked to figure out what is the probability density function. And it's a rather simple one because it is just, I mean, as long as the function is differentiable. What about in the discrete case? If I want to get the PDF from the CDF, so this happens in the continuous case. What happens in the discrete case if I want to have PDF from the CDF? So what should we do? How to get it? Their function.
So we just subtract the last value of CDS from the previous one.
Right. So what happens? Absolutely right. But what happens generally that we understood that our CDF is, for example, right continuous. So if you look at the difference of the value fa plus and fa minus, where plus and minus just correspond to the limit approachment from the right side or from the left hand side, then this guy will give us the probability of a. So some of you may also think about it like going from x plus a minus. So you are basically trying to take the difference of the values of the CDF, which is slightly on the right of this number or which is slightly on the left of this number. And then you will get the probability at that particular point. So CDFs can also be used to find out PDFs or the PMFs, just like if the PMFs and the PDFs are given, then you can find CDF. So they are sometimes interchangeably used. Different places have different uses. We will see when it will be used in a particular application. But one thing which is clear from the discussion which we are having, that we have one what we call as X, random variable, another what we call as some sort of a PMF or PDF depending on this, and the third function which is fx. Generally, we are given probability distribution of a random variable. Once the distribution is given to you, what are the things which you can get out of the distribution? There are several things which you can get out of the distribution. The most important one, what we call, is expectation value of the random variable. And this is defined as expectation value of random variable. I write capital X. This is a general way of writing it. And this is defined as summation xk pxk for the discrete random variable. And this will be defined as minus infinity to infinity x p. Okay, let me just write down full for continuous random. So now what we are talking about, once the distributions are there, what can you get out of it? For example, there is a Poisson distribution. What can you get from the Poisson distribution? What are the quantities in which we are interested in? So one of the quantities in which we are really very interested is what is called the expectation value of a random variable. Okay, and random variable can be anyone. Depending on whether it is a discrete one or whether it is a continuous random variable, you will have, of course, the corresponding expression. Now, please see, if I just look at the first expression, the summation one, what does this mean? That let's say there exist values x0 with probability px0, then x1 with probability px1, and so on and so forth, let's say. What kind of quantity this is? If you are talking about, and as an experimentalist, if you talk about this, what kind of quantity it is? That I am multiplying this quantity with its weight. Px naught is the probability that x naught is achieved, right? So some sort of a weight, that this is the frequency with which I get x naught, divide by the total frequency. So what kind of quantity is this in the experiments?
Mean, sir.
This is what we call as the mean. In fact, this is how you define mean. In case those of you who are thinking about it, this is if a given quantity is repeated f0 times, fn1 times, fn times, so on and so forth, then which is nothing but f0 plus f1. So you look into it, the expectation value of the random variable. Why it becomes important? Because this provides something what we call as the mean, and it is one quantity which can be very quickly checked. Kindly mute. Please mute. Yeah. So the expectation value, what we call, this is what we use in the probability for a theoretical distribution. But since this gives us something which has the experimental correspondence, which we call as mean or average, so it's common to even call the expectation value of a random variable as mean, mu. Now, for example, we discussed yesterday that there is a probability that electron can be found anywhere from the nucleus till at some place. But what is the expectation value of the random variable R? Which means what is the average value at which electron will be observed? So this is one question which will be very useful because there is a probability which is associated with all the distances. So one can quickly find out the expectation value E of R in that case using the formula which is given here, and one can check what is the average value at which electron will be found. So this is why the importance is that we can at least get certain things very easily. The other quantity which becomes very important from the experimental point of view is what we call as variance of a random variable, which we define as, can somebody tell me what generally they understand when I call the word variance? It is denoted by the sigma square.
Sir, it is the
Whenever, yep,
square
yep.
of, sir, it is the square of deviation from the mean.
So mean square deviation. Okay, good. Now, very good. Why that would be important? Because I said after
To
mean,
check
yep, yep.
how the how spread the values are from each
Yes,
other.
how the spreading is occurring.
How the spreading is with respect to, yes, from particularly from the mean. Now you can look into it. So I am writing down the formula. Please see that it is taking the x minus mu. Mu is defined as the expectation value. So explicitly I have written here also x minus mu square, and then take the expectation value. Fine. So when I am saying that I am going to take the expectation value, what will be its definition for the discrete random variable? So let's just write down. So sigma square will become what? K, k minus mu square pxk. This is as simple as that for discrete random variable, and minus infinity to infinity x minus mu square px dx continuous random variable. Yeah. So it's not only important to figure out the mean, it is equally important to think of whether a system has spread around that mean or not. For example, by this time you all know, if I, sorry, if I plot a distribution like this, any distribution, and if I plot a distribution like this, so let's say 1 is the narrowly peaked and 2 is the flat one. Which has large sigma? 1 or 2?
Second one, sir. Second one.
So the flat one.
Right. The
Flat one.
second one, sigma 2, is surely greater than sigma 1, which just tells that even the mean may be important in both the cases, but the spread around the value of the mean is so much in second case that there are plenty of times that the system spends in all the other places other than the mean also. Whereas in the first case, system spends considerably a large amount of time around the mean. Or if we repeat an experiment, we will get plenty of values with the mean or around the mean in the first case. Where the second case, it won't be the case. So it's not only important to know the mean, but how that mean is distributed. So measure of spread or variability around the mean. Now, with this, of course, variance is useful, but the quantity which we generally use is not variance. We use what we call as the standard deviation. So this is something which is basically coming out of the sigma square, which is what we call as the variance. And this standard deviation is nothing but the positive square root of the variance. So this is rather simple concept. Sometimes you will see the books write standard deviation of a random variable. Now it is important to note that what we are giving as the quantities here, these are all the parameters, or these are all the quantities which we are measuring in a probability distribution for a given random variable. It is just that since we are able to make the measurement with respect to, we are able to make a comparison with measurements. So certain quantities take more prominence than other. Mean takes, for example, very important position of any distribution because we are interested in generally getting this value. Okay, what is the average value at which it is? And I'm sure that when you were doing your nuclear physics experiment, I mean, you have started doing your Giger-Muller counter experiment yet or not?
Yes, sir. Yes, sir.
Yes, sir.
No, sir. Yes, sir.
So maybe
Not
just
yet.
one of the
Some of us, some
batches.
group have.
Oh, some of you. So, okay, I
Yeah,
mean,
so
I
we
will
have
still
different
take some time.
labs.
See, okay, got it. Yes, right. So, So what I will tell you that once I will be coming close to finishing this unit probability statistics, then I will discuss with you certain things about the nuclear physics experiment, because nuclear physics as governed by the laws of quantum mechanics, these experiments are mostly affected by our statistics related events, and hence probability and statistics play a very important role there. Okay, anyway, let's just do a quick question. So let me give you a random variable x, which is nothing but number of heads in a toss of a coin, single toss, and this coin is fair. So find mu, sigma square, and sigma. So by this time, you know mean, variance, and standard deviation using the definitions. So let's just write down what is the value which random variable can take.
0 and 1.
Very good. What is the probability? Px, PMF,
Half and half.
half
Half
and
and
half
half.
x.
Half and
X
half.
excellent. Now, what is the definition of mean? Summation x px.
Px.
So, what should be this? First value is 0 into
0
1
and
by
half
half.
plus
half
1
plus
into
1
half,
into half.
which is
Half into
Half.
half. Half.
half. So, the average value is half. And what will be the sigma square? So, okay, do this x minus mu now that you have got it, px. So x is 0 minus half square into half plus 1 minus half square into half. Do that.
Sir, 1 by 8.
Okay.
1 by 4.
Sir, 1 by 4.
So 1 by
So
4.
1
Yeah,
by
what
4.
will,
1
what
by
will
4.
happen? It will be 1 by 8 plus
So
1 by
1 by
8.
4.
So yeah, so you should get 1 by 4 and sigma 1 by 2. So if you want to get the standard deviation. So this is what it means when we are asking you to find the mean. The interesting thing is, since it's a toss of a single coin, then the mean will be what? I mean, since I have taken a single coin toss, so its probability is basically reflected in the mean. If there are more than one coin, if there is more than one coin, of course you will find that this number will start changing, but then you will start seeing that standard deviation. Now look into this. In a toss of a single coin, mean is half, which basically gives you an idea that the probability of getting head is half, but the spread or the variability around it is also half. So the certainty with which you are able to say that this a single toss is going to give you head will have plenty of spread around it. As you increase the number of tosses, you will find out that the mean should still be half for getting head in the case of a toss of coin, as long as it is fair. But this spread will start getting less and less. So if I have basically 10,000 tosses of a coin, then the spread around this high value half will be much smaller. So in the case of infinite tosses, ultimately probability should turn out to be exactly half. So that's what it is trying to reflect basically, that in a single toss, mean gives you that somehow the impression that it is half, but there is lot of variability, and hence standard deviation is very important quantity. By the way, the formula which we sometimes use for this is given in terms of e of x square minus something like this. So instead of finding out x minus mu square and then take the expectation, one finds out expectation of x square minus something. And how will you do it? Basically just expand this. So expand your bracket, x square plus mu square minus 2 mu x. So what it will become? Expectation value of the x square plus expectation value of mu square minus, okay, let's just write plus expectation value of minus 2 mu x. Now here what I am using, one, that expectation value of x plus y can be written as this. Okay, and two, find out expectation value of mu square. What will be that? Just use the formula.
That it is mu square.
So mu square px overall, okay, possible x values. I am just doing it for DRV, discrete random variable. You can do the same thing for the continuous, you will find out same. So what will happen now? Expectation value of mu square, so it is nothing but, so whatever is the argument, it will go here times px, but this mu square is independent of x. So I can write down mu square summation px. And what is summation px? Overall x values.
1.
This is equal to 1 because this is our probability mass function. So expectation value of a mu square or expectation value of any constant is the value itself. Because what it means that if you repeat the measurement, so remember what was the expectation value meaning, that if you repeat the measurement, how many times you are getting one value, how many times you are getting second value, how many times you are getting third value, and that's basically probability weighted. Now if a expectation value is taken for a constant, then what, how so many times you are going to repeat that experiment, you are going to get just the constant. That is what it means, that expectation value of a constant is nothing but a constant. Fine. So expectation value of this is 1. What about expectation value of minus 2 mu x? So let's just try to think about it. So like minus 2 mu x px. So what will be this?
So minus 2 mu can come out.
Minus 2 mu can come out, and then this
Minus
becomes what? S x
the
px.
rest
What
is
is this
mu.
guy?
Mu.
This guy is another mu.
Mu.
Right? So this will become minus of 2 mu square. So what will be our sigma square in that case? Let's just look at the expression. We have ex square plus mu square minus 2 mu square, which is equal to ex square minus mu square, or sometimes it is also written in the books as ex square minus expectation value of x whole square. So this is another common expression which we use for the variance rather than using directly the mean square deviation. So E of x square, where what is expectation value of x square? How will you write it?
Integral of x square px.
Right. Okay.
Summation of x square bx.
Right. I mean, depending on the variable which we are using, this is nothing but this, right, for the DRVs. And just those who want to be explicit, continuous random variable. Yeah, this summation or integration is over all possible x values. Please remember that. It is not over certain values, it is over all possible values which x can take. Okay, so let's continue with this. Something more. What about another interesting thing, what we call as mode? What do we call this as mode?
The maximum number of outcomes.
Yeah. So it is the value of the random variable for which Px is maximum. So when you are saying outcome, remember every outcome now that we define our probability as the number of occurrences of certain event divided by the total number of occurrences. So for which the probability Px is maximum, that value will give us the mode. This is the maximum frequency with which a particular number is repeated. Yeah. In the case of continuous one, it is rather simple to see because how will you find out at what point x is maximum? So how to find the maxima of a
The,
probability distribution?
Derivative.
the derivative.
Right. This is rather simple. So you take dpx over dx at x equal to x mod, and this guy is basically 0. And of course, d square p over dx square, that should also be less than 0 for the mode to be there. And then we talk of something what we call as median. What is median? So this is again mode of a random variable x, median of a random variable x. The quantities which you are using in measurement, now we are defining in terms of random variable for the random experiments, which are governed by the laws of probability. Like your Geiger-Müller counter, the counting statistics is governed by the law of probability. So this median is the value of x which divides px into two equal parts. So you should have half the values of px before this and half the values of px after that. Something like this. So probability x less than equal to x median, that is exactly half. So median is that value for which this probability is 0.5. Now, how do we define this? I mean, we have already defined something as this. Capital X less than equal to a random variable value.
The cumulative distribution
The
function.
cumulative distribution till there.
Right. So it basically means that fx median equal to 0.5. So what will be the probability of x greater than x median?
0.5.
0.5.
Half.
It is basically half, so it doesn't matter that which way you are going. In the case of discrete random variable, you may find some difficulty if there are number which is even versus number which is odd. But in the case of continuous one, you will not face any problem, as you know that exactly at a particular point you do not need to worry about anything. So since I am using strictly greater than here x greater than x med and x less than equal to x medium, so then you may understand that in the discrete random variable there may come out a problem if there are even number of observations, but that's what you have already encountered, I am pretty sure, in your maths class, maybe in 8th or 9th, when you try to figure out the median. Now, why sometimes median is used and not mean is used? Sometimes mode is used and not mean is used. Can somebody tell me? Just quickly, I mean. Median saves you from what? I mean, instead of using, because all are the measure of the central tendency. When I'm saying central tendency, it is the mean, how the average of the quantities are behaving. Now, see that the mean, the way mean is defined, mean takes care of things which are there even at the end values. Now, look at the definition of mean. So, if you just go back, so previous, this one. So look at the experimental or working definition of mean. Whatever x value it is taking, the probability you are multiplying with it. So even if an x value is extremely far off, you have made an error and you have got a result which is completely far off from what other values are. But when you are going to take the mean, your mean will be influenced by that value surely. So for example, you have taken three observations. One observation was 2, another observation was 1, and third observation turned out to be 60, 60. Will the mean be affected by that or not? Yes, no. That it will be
Yes,
affected
sir.
by this 60 value or not?
Will be, sir.
Yes, sir.
It will be, right? Because it is the third value. So when you are going to 1 plus 2 plus 60 divided by 3, this number is going to be a huge one. What about the median? Will that be affected by this 60? 1 to 60. What's the value which is coming exactly at the center? That is what you are going to do, right? So you arrange these values in ascending order basically, and then you say whatever the value which is there at the center, this is the value which you are going to pick. And in that case, 1 to 60. So which value you are going to pick for an odd number? It is rather simple. Median.
The center one.
The center one is what?
N plus 1 by 2.
Yeah, in this case, 2. So 2 is almost unaffected by 60. Not almost, it is unaffected by this outlier 60. Median generally gives you the behavior of the central portion without having effect from the edges or the outliers or far off extreme values. Mean is affected. So at times you will find out that certain distributions are described by median and not by mean, because those distributions may have the tendency of going to very, very high values at large of x. And we are not sure whether those values are real or they are coming from some fake ones. So anyway, that's general idea of having the mean median. It has nothing to do with probability statistics only here, but it is the general case. And for a symmetric distribution, perfectly symmetric distribution, what would be the values of mean, median, mode? Are they different or same? If a distribution is perfectly symmetric around the mean,
So they'll come out to be same.
It will be same.
it comes out to be same, identical. Do you know of any distribution for which mean, median, and mode, they are all identical? Any
Normal
Maxwell
distribution.
Boltzmann.
Maxwell Boltzmann and Gaussian normal. Okay, so we will see, but please remember, so you have used the word normal distribution. That means you have used this word somewhere, huh? The distributions, not as per se in probability statistics, but you have heard of this distribution. Where have you used this normal or Gaussian distribution?
Sir, wave packets.
No. Okay.
So, wave packet. Okay. Okay.
They're in the random
So,
variable experiments.
random variable
Hello.
experiment. Oh, so some of you did
The
the random variable
random
experiment.
error experiment. Random error experiment.
You did the experiment at the BSc level?
Yes, sir.
Oh,
Yes,
actually,
sir.
many
All
people-
of you did the experiment on the random errors?
Okay,
No,
please
sir.
tell me
No,
how
sir.
to
No.
get it.
No, sir.
Yeah.
No,
So
sir.
that's why I mean I will take. So okay, we'll not discuss it now, but maybe at some point in our additional class we should discuss that, because probability statistics, errors being random, please mute, errors being random has lot of implications coming from probability statistics. We use our laws of probability and statistics to describe errors, particularly the random error. So I'm not going to discuss it now. We will continue to make our progress. I defined certain important movements, not movements, certain important quantities without saying what they are called. And I am just now going to actually define it in terms of a very generic name. These are called algebraic movements and the central movements. In fact, whatever I was discussing up to now, they all come under this. The word algebraic movements, it just tells the expectation value of x raised to power n. And this is, again, I mean, the definition is pretty simple to think of. So x n p x dx, where the central movements are defined x minus mu n x minus, please look at the place where I am writing the capital letter and the one where I am writing the small ones. This whenever I am putting something within the expectation value, I'm always using the capital X, which is to show that I'm talking about the expectation value of a random variable. Whereas on the right hand side, I'm doing the actual calculation. So there the values come. Okay, minus infinity to infinity. x minus mu raised to power n px dx, where n of course is any integer. Now, this is a very general definition that once we find out the distribution, we find our algebraic and central moments. Now, central moments, as the name suggests, they are with respect to the mean, the expectation value mu, which is the first moment. Remember the moment which we discussed, what we call as, the mean or the average. Yeah. So now, if I ask you, when we discussed mean, mu, what exactly is that in terms of the algebraic movement or central movement? Is it the first, the second, first movement, is the zeroth movement, something?
The first movement.
First what? Algebraic or central?
Algebraic.
Algebraic.
First algebraic movement is called mean. So this becomes, as it is the first algebraic movement, hence it becomes very useful. I mean, basically you know that. What about the variance?
Second
Second central
first
movement.
central.
Second
Second central, sorry.
central movement. In fact, you already saw that since I can write down in terms of ex square minus ex square, that means I can write down my second central movement in terms of my algebraic movements also. Sure. What about the first central movement? What happens to first central movement? Expectation value of x minus mu. What will be this? So this should be expectation value of x minus expectation value of mu. So what will be this?
Sir, it is
0.
0.
Right. See, expectation value of x is mu. Expectation value of mu, which is a constant, is already mu. So this is, so first central movement is of no consequence, and you see it in your experiments, in the sense whenever you have a line and the points which are scattered around this line, and if you take just the errors and add them up, you say that some of the errors are positive, some of the errors are negative, then the total error will go down to 0 if I just take that. So instead of using x minus mu, you use this mean square deviation or root mean square deviation. And that's why sigma square, which is nothing but x minus mu square. So this quantity becomes so useful, that it is the mean square deviations. Yeah. So everything what we do in our experiment related with finding out the means, the standard deviations, they are basically nothing but finding out the algebraic moments or the central moments of a given PDF. So at this point, I should just summarize that we have just defined a random variable. We have defined PMF or the PDF of a random variable, along with, of course, our CDF. And then we are describing several important properties or the quantities which describe those distributions. So algebraic movements and the central movements are generally used to describe any particular probability distribution, maybe probability mass function or the probability density function. But this is what we use. And this is what you do in your experiment to compare that. Now that you will be doing certain, some of you will be doing this experiment of the counting statistics, you will be checking whether the counts which you are getting from the Geiger-Müller counter, they are coming from Poisson distribution or not. And in order to do that, all you are going to do is to plot a distribution, find mean of the distribution, find variance of the distribution, and check whether it is consistent with theoretical predictions. So this is what we do very commonly in our nuclear physics experiments. Even in the other experiments where you are not using the quantum mechanics, since errors are random, so you do this without knowing that you are doing it. Something like that. And that's why I said that we'll have to have one class, the additional class, where I will discuss with you certain important aspects of using the random distributions in describing the errors of the experiment. Since some of you have already done that, they may be aware of it, but others, okay, we are going to do it. Questions up to this point? Okay, no, so let's just go and define. I mean, these are something which is defined in the probability statistics book, and it's not bad to know those. So I would just define it like that. At this point of time, how am I going to use it? I'm not going to tell it to you. Fine. Depending on a particular distribution, we may use it or we may not use it. Now that we have some idea of the first algebraic movement, the second algebraic movement, the first central movement, the second central movement, the next algebraic movements which become important, they are all with respect to the mean, and hence they are all central movements. So for example, the third central movement, in fact, this is what we call as the standardized one. I am giving you the definition, and whenever this problem comes, we will have to basically calculate it. So alpha, I define it as alpha 3, and what it is. This is the third central movement, but now I am using the word standardized, so I divide it by sigma q. Can somebody tell me what happens if I divide something by this, where sigma is nothing but the standard deviation? So what, third central movement, fine. Why I would be standardizing it by dividing it or normalizing it by dividing by sigma q? Can anybody think of it? So let me just give an example. So let's say you are making a measurement of length. So like the way we were discussing electron. Yeah. Now that measurement will have some unit because you are going to make a position measurement, for example, right? So when we are going to make a measurement, then that measurement will come in the unit of length. So in terms of, for example, atoms, we talk about angstrom. If it is about nucleus, we talk about Fermi. If it is about macroscopic objects, we talk about centimeters, meters, and if we go to terrestrial, of course, we have light years. Yeah. So distance units are like that. It may go from one point to another. Temperature units are like that. You take any unit, it has the whole spectrum. Now look at what is happening on the numerator only. So when we are going to take the expectation value of x or any value which we are going to make out of it, then this expectation value will also have its unit. So if random variable is length, then expectation value of the x will also have the unit length, right? Now sigma, which is another movement, that will also have the same unit, which is the unit of the expectation value, not sigma square, but sigma will have same unit as expectation value. So if I divide ex by sigma, what am I doing in principle? I am dividing these units. So I do not need to worry about what is the unit in which I am measuring. I am making it something what we call as dimensionless. So by dividing it by sigma cube, we, or what we call as standardizing or standardized movement, we make our third central movement dimensionless, which is nothing but the measure of asymmetry. Now when I am saying asymmetry, it is something like this. If a distribution like this looks perfectly symmetric, then on a distribution like this doesn't look perfectly symmetric. Yeah, but we define the coefficient of this measure in such a way that it should not be dependent on any unit. And that is the reason why we divide it by sigma cube. So that's what we call as the measure of asymmetry. Homework for you is, there exists the fourth center movement, which is also very important movement for certain distribution. What is that, and what will be the definition of the standardized fourth central movement? So this, please do it as a homework. Tell me what it generally shows. So once I get my Px, I am interested in figuring out what kind of distribution it is. In order to describe it, I come up with first the central tendency, mean, median, mode. Then I try to check what is the variability around the mean. Then I try to check whether the distribution is symmetric or not symmetric, and something else. So those are basically contained in my movements. If I give you all possible movements for a distribution, then basically that takes care of the whole distribution. But the good point is, generally we do not need to worry about too many movements. It's the fourth movement up to which we go, and after that we say that largely we have understood our distribution, and let's just solve certain problems for that. So questions up to this point?
Sir, could you please do it again? Third central movement.
But third center movement, I gave you the definition, right? And I say that it is a measure of asymmetry. For a symmetric distribution, that means for a strictly symmetric distribution, like normal, this value will be
0.
exactly 0. And for any other distribution which is not symmetric, then it will tell us whether alpha 3 less than 0 or greater than 0. Depending on that, we will figure out that there exists symmetry around this mean. So there exists some asymmetry around the mean, and we try to figure out, okay, what kind of asymmetry, how big is that asymmetry, something like that. So this third movement. Okay, at this point, just taking a pause since we are doing plenty of definitions. Can somebody tell me why they are called movements? Or can somebody not tell me? Can somebody think of it? Where did they use the word movement for the first time? Word movement in physics.
Dipole moment, sir.
Dipole
Sir,
moment, okay.
that used in moment of inertia.
Moment of inertia, okay, good. So can you now think of why did you use the word movement there? What did you try to mean? Because interesting feature which I wanted to tell you, the mathematicians gained a lot by using this word. Remember that what we are describing is probability statistics, is a branch of mathematics. We use it in physics heavily, but it's a branch of mathematics. And the ones which we call as the algebraic or the central, they are, I mean, mathematicians ones. But the word movements came from physicists, from the moment of inertia. Moment of inertia is the first one when we started using it. So what was moment of inertia? Can somebody remind me? What was moment of inertia? What is inertia?
Inertia is the property to resist any change in the motion or kind of any without applying the force.
Okay, so that means in a translational movement, let's say if I am talking about movement in a single line or a uniform motion in a straight line, then what property of an object defines that inertia?
Sir, it's mass.
Its mass. So if it is more massive, it will require you more force to move. Once it is stopped, so it will require more force to give. So that is the mass, right? What about the rotational motion? What happens in that?
So the distribution of mass around the center of its mass.
The center of mass and the distance square of the distance.
Right. So the word movement was used at that time. I mean, interestingly, since the movement of inertia it depends on the distribution of the mass. Now you can understand that we are talking about the mass distribution. So it can be reflected by some distribution, what we are talking about in probability statistics, and the movements basically. So when we are saying the distribution of the mass, it is nothing but how different points are associated and what is the mass composition at those points with respect to that particular point. And in the rotational motion, this distribution of the mass plays the same role which the bulk quantity mass was playing in the uniform motion, right? And the word movement was taken from there. That means that in the algebraic movements when we discuss, or the central movements we discuss, mathematicians picked that word from the physicists. So that shows the interlink between the physics and mathematics development, where we are describing that where we are trying to emphasize that a distribution is characterized by its movements, which means that how at different x points our probability px is given. Even in the mass distribution, you can try to convert it in terms of the probability distribution or your Maxwell Boltzmann velocities. There I said that the random variable is velocity. So it is just that depending on what random variable we are talking about, correspondingly the probability distributions we are talking about, they all come under the same umbrella again. So the word movement is picked from there. That these are defining certain important characteristics of a distribution. Okay, so let's just, I will take up a question, I mean, most likely in my additional class next week, in order to basically emphasize or have certain calculations coming out of it. So I am giving more and more of the definitions, to be honest, at this point of time. Now, in the some simple distribution, I wouldn't say they are simple, but they are very useful distributions. DRVs and CRVs. So the next point is that I am going to take two of those discrete random variable distributions and try to just find out some parameters, maybe mean, standard deviation, variance, something like that, and see how it goes. What do we do in physics? Basically, that's the idea here. And then in the continuous case, we are going to take two distributions. Okay, sorry for this handwriting. Oh, normal, let me. Yeah, so Gaussian distribution and the normal distribution, they are basically same. Gaussian distribution is called normal distribution because of the importance. Yeah, so we are going to take few distributions, both for the discrete random variable and continuous random variable. We will describe those distributions. They are important in physics. We'll describe the distributions. We'll see what will be the several things which will come out of it. And that's what we do whenever we have a probability distributions. Okay. So in today's class 1056, I would just define my binomial one. I will not finish it off. I will just start it. So first distribution which we are going to pick. Can somebody tell me whether they have heard of this distribution? Binomial distribution?
Yes, sir, in statistics.
Okay. You all had a course in statistics?
Yes,
In
sir.
our
And
no, sir.
Distribution was there also.
No, sir.
No, sir. Okay, so some of you may say it. So one person has said that in statistics they have used it. I am more interested in physics. I mean, did you use this binomial distribution in physics? So remember
Sir,
whenever,
while doing sorry, it's a certain theorems, like I don't exactly remember, but it was there in certain theorems, residue theorem and all, while we were studying it in some semester.
okay.
It was
Okay.
somewhere
generally in mathematical
in
physics,
expansion.
Advanced numerical. Yeah,
Fourth
I
semester
mean
or
this.
third semester.
Yeah,
Think so.
got it. The issue comes to me is like this. Remember that we are physicists. I mean, we are reading our mathematical physics. Our perspective is that we want to understand something, but then there has to be a reason for that. Of course, one is that if we understand the underlying mechanism, then we will be able to solve several problems. Yeah, sure. But now that we are studying particular distributions, there must be some physics reasons for that. Fine. So at this point, I will just tell you what the binomial distribution would be. Or whenever a distribution like that comes, you will say, okay, sir, we will apply binomial distribution to that. So idea is from that perspective. So let's just see what the binomial distribution is. But we have to have some long-term understanding of where the binomial processes are there. What you have generally heard, I can tell you, is binomial coefficient surely, which what we call as, let's say, of the kind ncx. So n factorial, x factorial, n minus x factorial. This coefficient is called binomial coefficient because it comes in the expansion of this guy a plus b. So if you have two monomials and you have raised to power n, and if you want to expand it, you will find out plenty of terms of the type this. Yeah, and that is why it is called binomial coefficient. In fact, one can extend this to a plus b plus c plus d and n, and then this binomial coefficient is then called, when I extend the same thing to many such monomials, multinomial coefficient. Okay, so this, so okay, you haven't done that. We'll see. Anyway, so let's just come back to binomial distribution. What do I want? What am I interested in? I am interested in certain number of successes, and I will explain that. Wow. Okay. Number of successes in fixed n number of trials. So for example, so maybe toss of a coin. I am interested in seeing how many times I define my random variable as head, and I say how many times I am getting head. So out of fixed n trials, how many times I am going to get head. That may be something which I am interested in. Now, what's this process is governed by? This is interesting to note that each trial results in one of the two disjoint outcome. So only two possible outcomes are possible: success or failure. And those are disjoint. So if success occurs, then failure doesn't occur. If the failure occurs, then success doesn't. If the head comes, then it is tail is not there. If the tail is there, then it is not head. Yeah, something like that. So in a given trial, there can be only two and two possibilities. And out of those two possibilities, if one possibility is occurring, the other cannot occur. Okay. Probability of success in any given trial is fixed as P. So if I am tossing a coin, then in first toss, the probability of success is half, if it is a fair coin, of course. In 10th toss, it is still half. In 100th toss, it is still half. So probability of success is fixed to be P. And of course, this P will be 0 less than P less than equal to 1. What will be the probability of the failure, by the way?
1 minus
So
P.
1 minus P.
Yeah, that will be simple. How it is 1 minus P? Because your S union F gives sample space, your S intersection F is disjoint. So, of course, I do not need to dwell on that. And only one more thing. Trials are all independent and identical. This is what we call as IID. ID, independent and identically distributed. So I will write it later on, but okay. My idea is to just tell you something. Whenever I am interested in having certain number of successes or want to figure out the probability of certain number of successes in n fixed trials, such that each trial can result in one of the two disjoint outcome, and probability of success in any given trial is also fixed to be p. In these cases, we use binomial distribution. So only two possible outcome, either this will or that. Now, can you tell me in physics where this situation arises? So are you ever interested in figuring out in certain physics processes that the process, either the process can occur or process cannot occur, and there is a fixed probability associated with that? Have you ever been interested in something like this in physics?
Sir, can you please repeat?
Yeah, so binomial distribution is applied in those cases where we are interested in figuring out certain number of successes in some fixed number of trials. Fine. So it's kind of the experiment. What kind of experiment? In which only two outcomes can come, and the outcome is such that the probability of the success, I mean, we are defining those outcomes as success or failure, we can define it as anything, but the probability of success is fixed in each of the trial. So I have already given you toss of a coin. So if you do this experiment, random experiment, there the binomial distribution will surely fit in, right? Because this is the toss of a coin. Number of trials I'm fixing. Each trial results in either head or tail. Probability of head in a given trial or probability of tail in a given trial is fixed. Probability of the other one is 1 minus p, and trials are all independent and identical. So if I am doing a random experiment of tossing a coin many times, then binomial distribution will apply. This is one place. Can you give me any other place in physics where this distribution will apply?
So can we take uncertainty principle?
No, I mean, you are talking about an experiment right now. Uncertainty principle in principle, I mean, to be honest, will be application that I will be figuring out, say, a random variable x, fine, and then I will be figuring out uncertainty in a random variable x, so sigma x. So I will somehow figure out the standard deviation, and then I will do the standard deviation of the momentum, sigma p. I will multiply the two, and I should see that I will be obeying the uncertainty principle, right? That's what it will be. I will give you an example and then you will understand that. But here I'm interested in the experiment itself. What experiment in physics, any process in physics, any experiment in physics in which there are only two outcomes and the probability of a given outcome is they are all independent. You
Decay
are
of a
doing that
particle.
experiment.
One
Decay of a
orbital is
particle.
with
In fact, this
electron.
is, yeah. So there are two places where you are even right now using it, particularly those who are doing it in the nuclear physics experiment. When you are talking about a nucleus decay, either a nuclear, so radioactive decay of a nucleus, you can understand it either the nucleus can decay or not decay at a given time instant. It cannot happen that it will decay or not, I mean, to get together. Yeah. So there are only two choices, either the nucleus decays or it doesn't decay radioactively. The probability is fixed for a given nuclei, for a given set of nuclei. We have this probability is fixed. That is what you basically govern by the average half-life of a nucleus, that in this many time, how many of these nuclei will give. So radioactive nuclear decays, they are basically following binomial distribution surely, because there are only two possible things, whether the nucleus decays or whether the nucleus does not decay. So binomial distribution, of course, can be applied there. Except that we do not apply directly the binomial distribution. We apply something what we call as, so now, Poisson distribution. Have you heard this word or not?
Yes, sir.
Yes.
Yes,
Okay,
sir.
but the idea is, okay, what idea is that next time whenever people think about any experiment in which there are only two possible outcomes per trial, and the probability is fixed, you will say that I can apply this particular distribution binomial. So another homework, which is a physics related, is not exactly your homework related, but try to figure out the situations where you use binomial, Poisson, uniform, or Gaussian. These four I have basically picked because these are very important in physics. And we will just see, develop our theory. I mean, we'll first define our probability mass function. We'll see that the probability mass function has to, of course, obey certain rules, whatever rules they are supposed to. And then we'll find mean, we'll find standard deviation, things like that. We'll do that for the Poisson distribution, uniform distribution, Gaussian distribution. Okay, questions?
Sir?
Yes.
We were specifically told in our nuclear labs that we cannot use binomial distribution and we have to use Poisson distribution because the number of trials cannot be known in nuclear decay.
Yeah, but we will come to that. We will come to that because I mean, it is way too early to speak about it. But the situation which I have given to you for the binomial distribution, whatever I have written for binomial distribution, they all apply exactly as it is. So at this point of time, you are kind of maybe some sort of a confused person, that one teacher is saying that I can use it and another teacher is saying I cannot use it. I will come to that. Of course, since I have to deal my Poisson distribution, I will explain what it means there.
Okay, sir.
Will it be fine? I mean, let's just keep building our curiosity a bit more.
Okay, sir.
Fine, fine. Okay, okay, we'll build that. Thank you, guys.
Okay, sir. Bye.
Bye.
Thank you, sir.
Thank you, sir.
Thank you.